Okay, so in this class we're going to talk about directional derivatives. We won't really touch on the gradient here, but I wanted to title it the same thing that this section is titled for the rest of the materials. So let's go ahead and jump into this. So a little notation here to get us started. So let's consider a function of two variables, just z is equal to f of x, y. And we're going to want to start working with vectors with our functions now. So this is going to inspire some notation here. If I have a vector, which is ai plus bj, we're going to write f of v. That just denotes we're going to take the x value to be the coefficient of I and the y value to be the coefficient of j. So f of v is just f of ab. So this just shortens a little bit of the writing, and it's going to make some of the notation a little bit easier for us. So for example, if I write f of v plus h times j, this is really the same thing since v is ab and h is just, or v is ai plus bj and h is just hj. The x or the I component is just a and the j component is b plus h. So I can write that f of a comma b plus h is f of v plus hj. So now let's recall we did partial derivatives before. And what I want to do is I want to reframe these partial derivatives in terms of our vector notation. So if I let v be ai plus bj again, the partial derivative of f with respect to x, remember this was just, we took the a and we took a plus h comma b minus f of ab. So with this new notation, this is just f of v plus hi, because that's only affecting the x component, minus f of v over h. And similarly for f of y at ab, we have f of v plus hj minus f of v over h. So this just takes the partial derivatives we're familiar with and puts it in this new vector notation. So nothing really new here, just new notation. But we can think of this now. Remember, when we introduced, say, the partial derivative with respect to y, we said this was measuring how the function changes as you change y. Well, in this case, we can see, rather than just saying it's the way the function changes when we change y, we can say, well, it's the way the function changes when you move in the j direction, which is the same thing as saying you change y, but it's a vector language for this. So we can view this graphically. So this orange curve here again is the curve where we fixed an x value and the y values are changing. So we can see what we're doing is I've graphed the vector j here. So f sub y is just saying if I'm standing at any point on that orange curve, when I take the partial derivative with respect to y, I'm asking what's happening when I go in the j direction. So we can see at this particular point, if I were to walk in the j direction, the orange curve goes down, so the function is decreasing in that direction. So this is just, again, this is another way to view partial derivatives, only with vectors now. So when we do this setup, it seemed very clear when we did partial derivatives, well, we could change x or we could change y, and both of those made sense. But now when we change this to say, rather than thinking of changing x or y, we're asking for the change in the I direction or the change in the j direction. Well, then easily we can say, well, why would we only be able to change in those two directions? If we go back to our picture, say, when we're standing at that point there, we could go in the j direction, we could go in the I direction, but there's infinitely many other directions we could consider that we might be interested in how the graph is changing in those directions. So why wouldn't we be able to consider how the function changes going in other directions? So let's take a unit vector. So u hat, here's our unit vector. u1 and u2 are our components. And let's ask, how are we going to define the derivative in the u direction? So I want to know, how is my function changing in the u direction? Well, the easiest way to view this is to view it in terms of the vectors. So we directly generalize here. Before we had f of v plus hi or hj if we went in the I direction or the j direction. Well, now I want to go in the u direction, so I just take h times u. I put a subscript with my f to indicate that it's the the derivative in the direction of u, and it's just this natural definition here. And if you do want to write it without the vectors in there, you can do that as well, and it's just given by the second line there. It's not quite as illustrative of what we're doing, but it does work if that's more comfortable. You really do need to get used to the first notation, though, for what's going forward. And what we can see from this is if I were to take u to be I hat, this would be exactly the definition for the partial derivative with respect to x. And similarly, if I took u to be j hat, we get the partial derivative with respect to y. So we could rewrite that partial with respect to x as f sub I ab instead of f sub x if we like to. We get the same thing there. So that shows us that this directional derivative, which is what this is, it's the derivative in the direction of u hat. This is just a generalization of the partial derivatives that we've already seen. And here's a couple of pictures with the graph just rotated here to be able to see in different directions. So we can see now what I'm doing is I'm saying, well, I want to go in the u direction. So it looks a little bit, the reason I included two pictures here is it looks kind of like it's going in this direction because of the 3D. But if we look at this one, we can see it's actually, this u is pointing exactly in the direction of this orange curve. And so this is asking if I'm standing at this point, what happens as I go in this direction? So I'm going to go down this curve here. So it looks similar to what happened in the j direction, except for now we're going across this curve that's in the direction of u instead of in the direction of j. But the exact same idea. So basically you can think of you're standing at that point and you're asking what's happening. And this kind of leads us back to, if you remember from the very first slide, there was on the title slide, there were two people walking on a mountain, which seems bizarre for why we would have that for a calculus class. But what we want to think of here, one of the kind of ways to view this, is if you're standing on a mountain and you look in a direction, is the mountain going up? Is the mountain going down? Is it staying the same height? So this directional derivative you can think of as if the function is the height of the mountain at the point, the directional derivative is going to tell you, are you going down? Are you going up? Are you going down a lot or only down a little, and so on. So the mountains are kind of a way to visualize what's happening with this. But just like before, viewing these things in 3D can be a little bit more difficult, so sometimes we like to use contour plots for this. So we can see here, this is a contour plot of a surface, and if we look at this point up here, and we're standing at this point, and we have our vector pointing in the j direction, we can say, well, what would the directional derivative be going in this direction? Well, we can see this curve here is 2, this next curve is given by 0, and then this curve is given by -4. So if I walk in the j direction, the values of the function are going down, so the directional derivative would be negative. We'll also see in class how we can estimate this based upon, well, how far are we changing in this direction and how much does the function itself change. We can estimate those values of f of v plus hj or hu minus f of v over h. So we can get an estimate from these contours as well. And let's look at one more picture, because this would just be the partial derivative in the j direct, or in the this would be the partial derivative with respect to y is what we'd be measuring here. But with this one, we can see we're at the same point, but now we're going kind of in the I plus j direction. And so we can say, well, we're still decreasing here, but notice in this case, my vector happens to be perpendicular to this level curve. And we can see this is the same length as the first one, and this vector is going, this vector doesn't quite reach the -4, and this vector of the same length gets past the -4. So if I walk an equal distance in this direction, I'll go down much further in elevation than if I walked an equal distance in this direction. And we'll see that's always going to be the case, that we'll see in lecture that if you walk perpendicular to a level curve, that's going to be your fastest ascent or your fastest descent. So that's going to be an important point as well. This gives you an idea of what the directional derivative is. The gradient will be introduced as a way to actually calculate this. So we define this directional derivative in terms of the limit as h goes to 0. And as we saw with partial derivatives, and as you saw with derivatives in Calc 1, we don't actually want to have to calculate that limit if we can avoid it. So the gradient will give us a way to avoid having to do those calculations.